Welcome back. In the previous video, we learned about Nash equilibrium. Now it is time that we look at some simple examples and obtain the Nash equilibrium or insert any for them. So here is an example. There are two players. Player 1 can either play U or D and player 2 can play either L or R. And because there are two actions each for both the players, so there are four possibilities, and this table has given the payoff very succinctly. So how can we obtain? Now there are two ways to obtain Nash equilibrium. One way is to hypothesize that this particular strategy profile or action profile is Nash equilibrium, and check whether they can become better off by deviating or not. If they can become better off by deviating any one of them, then the proposed action profile or a strategy profile is not Nash equilibrium. That's one way. So let us do that. So there are four possibilities. We should check for all: U comma L, U comma R, D comma L, and D comma R. We can propose that we can start with D comma R. Let us do D comma R first. This is the Nash equilibrium. Can anyone do better by deviating? So first let us understand the working principle, and then we should understand why does it work. So how can, if player 1 deviates, what is going to happen? Player 1 has decided to play D, player 2 has decided to play R. Player 1 has no control over what player 2 is doing. So player 1 will take R as given, and if player 1 deviates, player 1 will change the action from U to D. So parallelly you will change the row. What's happening? The payoff is going from 6 to 8. So of course player 1 has incentive to change the behavior. In other words, when player 1 is maximizing, what should he pick here? If player 2 is playing R, that's what we are trying to do, isn't it? Maximize with respect to player 1's action. Which action should he pick so that this entity is maximized? So he can either pick U or he can pick D. If he picks U, the payoff is 8, and if he picks D, payoff is 6. So he should have picked U and not D, and therefore by changing the action he is becoming better off, and therefore this is not a Nash equilibrium. How about this box? Let me change the color. How about this box? This box, let us say that does player 1 has incentive? Player 1 doesn't have incentive. We just check that when player 2 is playing R, U gives 8 and D gives 6. So U is more than D. So player 1 doesn't have any incentive to change. But how about player 2? Player 2 has the problem that player 2 wants to maximize, given in D comma L, that, or sorry, we have picked U comma R. So player 2 will take U as given, that's coming from player 1, and player 2 has to decide what to do here. L can be put here or R can be put here. L will give 4, R will give 2. So L is clearly more. So player 2 would like to change the action from R to L if given an opportunity, and therefore this is not an equilibrium. How about this box? Let us change the color once again. Player 1 changes the behavior. The payoff to player 1 will become 2. It was 4 earlier, so it's not good idea for player 1. How about for player 2? Player 2 can move here from L to R, and the payoff is decreasing from 4 to 2. So player 2 would also not like to change, and therefore we can say U comma L is a any. We can play the same game once again and use the second technique, which works. Sometime this technique works well, sometime the technique that I am going to show is easier to work with. What we do? We player 1 figures out the best response given player 2 is playing L. What is the best response from player 1? Best response is to play U, because U will give 4 and D will give 2. So, U is better. And if player 2 is playing R, what is the best response? The best response is again U, and I will come to that in a moment. But before we complete from player 2's best response, we should obtain that if player 2 thinks player 1 is playing U, the best response is L, and if player 2 thinks that player 1 is playing D, the best response is L. And therefore, in this box U comma L, U is the best response of L, L is the best response of U, and therefore U comma L is any. By the way, what we just saw, that player 1 has a dominant, if you pay attention, that player 1 has a dominant, strictly dominant strategy, and that is U, because what we saw, no matter what player 2 is doing, U is always the best response. What it means? That player 2 cannot do better than U ever. So, U is the strictly dominant strategy. Player 2 also has a strictly dominant strategy, and so basically this U comma L is not only any, and it is a strictly dominant strategy, strictly dominant strategy equilibrium. By the way, this is a good thing. Let us say if we had obtained this box as a strategic, strictly dominant strategy equilibrium, and this box as Nash equilibrium, then there would have been a contradiction. But anyway, we will discuss the relationship between strictly dominant strategy equilibrium and Nash equilibrium later. But what I am saying, it is a good thing that both are pointing in the same direction. Further, if you have not noticed, let me draw this game once again and tell you that this is nothing but a prisoner's dilemma. You can say there is no prison, there is no minus sign. How can we say that it is prisoner's dilemma? What is the requirement for prisoner's dilemma? That each player should have a strictly dominant strategy, and the equilibrium that you obtain is not the best for both of them. So, here it is 4 comma 4 they are getting. If they both were here, they would have obtained 6 comma 6. So, instead of taking a number, if we use symbol, then we can give the general formula in much better way. So, let me write it. Let us say here is up, down. Again, name could be anything, names are not important. L, R, we have A, here D, D, B comma C, C comma B. Another thing, another requirement for prisoner's dilemma is that game is symmetric. So, whether you put player 1 as a row player or column player, as long as you are doing it diligently, nothing would change, you will get the same game. So, it is a symmetric game. So, what is a requirement? That A should be greater than C and B should be greater than D. If you want U to be a dominant strategy, strictly dominant strategy, then this is the requirement. And you want this outcome to be better than this outcome, so then the requirement would be B comma D, but D has to be better than A, and A is already better than C. So, this is the requirement. So, either this is one possibility, but what is so special about U? We can make even D the dominant strategy, and when will it happen? So, if C is greater than A and D is greater than B. So, of course, this is what they are going to play, but in that case A has to be better than D. So, this will lead to C is greater than A is greater than D is greater than B. So, this kind of setting with either 1 or 2 fulfilling one of these two requirement will give you prisoner's dilemma. Let us look at another game. I do not remember whether I talked about battle of sexes or not. Here, let us say a boy and girl, they meet on a bus and they decide to meet again in the evening. They can go for either a movie, or they can go to a place where they can watch cricket match. We can put girl here and the boy here. These are the two options they have. It seems because they like each other, they would like to spend time together. So if one ends up watching movie and another ends up watching cricket game, then they don't get any payoff, so it is zero. Girl happens to like the cricket match more, so girls get higher from watching the cricket match, but boy is also spending time with girl, therefore he also gets some payoff, but boy likes the movie more, so this is what we have. Now we have to obtain the Nash equilibrium of this game. So we can go the best response route. Girl, if what would be the girl's best response if boy is playing M? The best response is M. And what would be the best response of girl if boy is going for cricket? Is also to go for cricket, because if girl goes for movie, payoff would be zero. You should check for the other way also, that if girl is going for movie, the best response from boy is also movie, and if girl is going for cricket, the best response is also cricket. So in this box they are playing each other's best response, so then none of them will have any incentive to change. So M comma M or C comma C are two Nash equilibrium in this particular setting. Okay, you could have used the other technique also, that would have given you exactly the same result. Now we have obtained this result, we can always check M comma M whether it is a Nash equilibrium or not. Let us say if boy is deviating, boy can change from movie to cricket, boy's payoff is the second number, and that is 0. So 2, it falls from 2 to 0, therefore boy will have no incentive to change, given that girl has gone for movie. How about girl? Girl changes, then again her payoff also decreases to 0. So C also doesn't have any incentive to deviate, and therefore M comma M is a Nash equilibrium. Let us look at the next game. This is called stag hunt game. Stag is basically deer. In English, deer has hiran, that's in Hindi. It has a different name, that's called stag. And the story is coming from a philosopher, Rousseau. I hope the spelling is correct. Rousseau. And he talked about social contract, that how social contracts are formed. So let us say two people are, of course he was talking about in larger setting, but here we have just two people. Two people are going to jungle to hunt. They have two options, either to cooperate with one another and try to hunt stag, and other option is to not to cooperate with one another and hunt rabbit. So in a way they both have two options to go for stag or rabbit. The issue is that stag is more valuable, but the problem is that it requires coordination between these two people. If they don't coordinate, then they cannot capture a stag. While rabbit is a small animal, one of them on his own can capture the rabbit. So the payoff would be, let us say high payoff, if they both try to capture stag, they would be successful, and let's say their payoffs are 8,8. If one goes for stag and other goes for rabbit, the person who has gone for stag will definitely not able to capture it, because it requires more coordination. The person who is able to capture rabbit will get the payoff of, let us say, 4. And same here, it is symmetric, 4 comma 0, and in this box both have gone for rabbit, so they will get 2 comma 2. What are Nash equilibrium of this game? Let us check. There are two possibilities. We can say, let us do here differently. Stag in short is S, stag stag, and R R. I would say both are Nash equilibrium. Let us check for stag and stag. If player 1 tries to deviate, player 1's payoff will decrease from 8 to 4. They are in this box for stag and stag. So clearly player 1 would not like to deviate. How about player 2? If player 2 changes from stag to rabbit, they will come to this box. Remember, when we are talking about player 2, we are taking player 1's action as part of the environment. We take that it's not changing. So from 8 it will become 4. So second player also doesn't have any incentive to deviate. So in SS, none of the players have any incentive to deviate, and therefore SS is any. Now the second is RR. RR doesn't look so promising. In stag they are getting 8 and 8, but in RR, rabbit they are getting just 2. But let us check. Can player 1 be better off by deviating? When player 1 is changing, player 1 can change from rabbit to stag, but player 1 has to take what player 2 has given, and so if changing will lead to a decrease in payoff from 2 to 0. How about for player 2? Player 2 also changing will lead to a decrease from 2 to 0, and therefore none of the players have any incentive. So RR is any. Few things we should note: that we are not allowed to move diagonally. This is not allowed because this requires coordination. Remember, our assumption was that each player is for his own or her own. Okay, each one is maximizing given what others are doing. They are not forming a team and deciding. That can be a case, but that we need to move to cooperative game theory to talk about that how the gains should be distributed there, because there we take that team formation can happen. So we are not getting into that part. Here we are saying that each agent is deciding on his own or her own. So that's why diagonal movements are not allowed. One can unilaterally deviate given what others are doing. One can change his or her behavior, and one will change if it makes that person better off. So that's what we have to keep in mind. Second, another confusion that we have: randomly we have put these numbers, but not so randomly. Nothing would have changed if we had put number 9 and 9 here. So of course we want a particular setting. In like stag hunt game, we know the character that there exists two Nash equilibrium. So to illustrate that, I have given you number. In real life, of course, when you are dealing with businesses, finance, so market will give you data. If you are dealing with engineering problem, the resources constraint will give you data, and you will have to deal with the actual number. Here these numbers are just made up numbers to understand the concept. So don't worry that much about the number. Let us move to the last simple example that we would be doing is hawk and dove game. So let us say there is a road, a motorbike is coming from this side and motorbike is coming from this side. They have, each one of them have two options: to continue driving or change their path. Okay, these are, a motor is coming, and then what we can say, that we can write the payoff. Again, this is made up payoff to understand. They can behave like hawk or dove, hawk or dove. What would be the hawk like behavior? They continue driving on it, but the end result would be that they would collide and they would harm one another severely. Dove like behavior would be that to change path, and it would be best for both of them. But if the person who changes his path will lose his reputation, that's why it's also called the game of chicken. will lose the reputation. Other could be that both change their path, then no one will lose reputation and they will be safe also. So let us say that the value of reputation is V and the cost of accident is C. So if they continue driving on the road, both of them, they both get V minus C by 2, V minus C by 2. We should also assume that C is greater than V. It is very, very costly to continue doing that, because if we don't assume C greater than V, we take C as less than V, then I tell you that you will have the prisoner's dilemma game. That's why we are assuming this one and not this one. And so if one acts as a hawk, he gets all the reputational value, that is V, and here it is 0, and it is here 0, and it is here V, and here they split the reputational value. I think there was a movie in which there was a scene also where two teenagers were driving towards one another. I think the name Game of Chicken is coming from there. So here we will try to obtain what would be the Nash equilibrium. Notice, if C is greater than V, then V minus C by 2 is going to be less than 0. We will assume that V is greater than 0 and C is also greater than 0. So this is less than 0, this is less than 0. So if player 2 is acting like a hawk, you are better off acting like a dove, because at least you are going to get 0, not negative here. And if player 2 is acting like a dove, then you must act like a hawk, because that will give you V twice more than V by 2. And similarly, we can check from other players' perspective and you will get this. So what is Nash equilibrium? The Nash equilibrium is that one person acts as a dove and another person acts as a hawk. Okay, so two setting in which player 1 is acting as a hawk and in the second player 2 is acting as a dove. So these are two Nash equilibrium. Right now we have focused on obtaining the equilibrium. What does it mean? What are the problems with them? What are the beauty of obtaining this Nash equilibrium? How do they predict the real life behavior? We will concentrate on these questions later on. Right now in this video we have learned how to obtain Nash equilibrium. See you in the next video. Bye.